This chart maps out 50 essential algorithms, and down in the deep learning category, we find algorithm 39, long short-term memory, or LSTM. It sits directly next to traditional recurrent neural networks, but it was designed to fix a fatal flaw in how they process sequential data. A standard recurrent neural network handles sequences, like text or time series data, by looping a hidden state from one step to the next. It takes an input, updates its internal context, and passes that context forward. But imagine trying to read a thick technical manual where you are forced to give equal importance to every single word, unable to prioritize a key formula over a minor preposition. What if the network had a memory it could deliberately choose to keep or discard? Looking at this diagram of an unrolled RNN across multiple time steps, we can see the exact structural problem. The network's entire hidden state is rewritten at every single step. As the network calculates its error and propagates it backward through these continuous rewrites, the signal is multiplied over and over by the weights. Because these values are typically less than 1, the signal decays exponentially. By the time it reaches the early steps, the gradient approaches 0. The network literally forgets the beginning of the sequence. To process large datasets, we need an engineered system tracking dependencies across thousands of steps, ensuring the error signal survives the return trip without fading. Instead of forcing a single hidden state to constantly rewrite itself, an LSTM splits the architecture. It adds a secondary, dedicated track used entirely for long-term memory. This chart compares the two approaches. On the bottom track, the LSTM's separate long-term state acts like a continuous conveyor belt. It preserves the error gradient near a stable 1.0 across thousands of discrete time steps. By shifting from a system that multiplies a decaying signal to one that adds values to a preserved state, the LSTM creates a constant error carousel. This physical architecture bypasses the amnesia that limits traditional sequential models. This diagram exposes the internal anatomy of a single LSTM cell. At the bottom, two streams of data enter: the short-term hidden state from the previous step and the new input token for the current step. These flow up into a series of learned gates. The first is the forget gate. It uses a sigmoid function to output a number between 0 and 1, acting as a valve that decides exactly what percentage of the old long-term memory the cell should erase and what it should keep. Next, the cell drafts new information. The candidate layer evaluates the current inputs and proposes a new set of values to potentially add to the memory. But those proposed values do not go straight in. They hit the update gate, a secondary valve that determines exactly how much of that drafted candidate data is actually allowed onto the main line. Then we reach the critical mechanical step. The old state is multiplied by the forget gate to drop irrelevant data, and the new, filtered candidate data is strictly added in. That specific additive math is what saves the gradient from vanishing. Finally, the output gate takes that newly updated long-term memory, runs it through a filter, and slices off a specific portion to expose as the short-term hidden state for the current step. Looking at a standard neural network schematic, we can map this exact theoretical flow into a working circuit. The sequence of sigmoid and tanh blocks visually confirms how these mathematical valves stack together to control the flow of information. We solve sequence amnesia by giving the network mechanical valves to choose exactly what to forget, rather than forcing it to memorize everything it encounters. Because these mathematical operations are packaged into a unified cell architecture, developers do not need to wire these individual gates from scratch when building out an application. The beautiful part is that a modern framework hands you all of it in a single line, and that line on a real dataset is where this gets concrete. When you write a single line of code in Keras to build an LSTM layer, you're invoking a high-level abstraction. If we strip away that framework, the underlying logic of the cell is defined by exactly 6 lines of fundamental arithmetic. Executing one pass of this cell requires 3 specific inputs. We need x, the current token, we need a prev, the short-term running context from the previous step, And we need CPREV, the long-term memory highway. The first operation inside the cell concatenates the short-term state and the current input into a single unified vector named Z. Because Z is the foundation for every subsequent operation, every gate inside the cell is forced to evaluate the running context and the brand new data simultaneously. With the inputs merged, the cell delegates its logic to 4 parallel operations. These are the equations for F, U, G, and O. All 4 lines share a deep structural symmetry. Each takes the exact same vector Z, multiplies it by its own learned weight matrix, and adds a bias. The difference lies in the activations. The forget, update, and output lines use a sigmoid function. This squashes the values to between 0 and 1, allowing these variables to act as soft valves that decide how much signal to pass. The G line is the outlier. It uses a tan-H activation to output a value between -1 and 1. This acts as the candidate data, proposing proportional changes to the memory state. The challenge for the network is using these 3 violet valves and this single candidate to update the orange long-term memory state without completely overwriting it. This line of code defines the new long-term cell state, C. Notice the addition operator. Unlike the multiplication-heavy steps in a vanilla RNN, addition has a derivative of exactly 1. This creates a path where the error signal can circulate backward through hundreds of time steps without decaying, what researchers call the constant error carousel. Finally, the newly updated long-term memory is squashed by another tan-H and filtered by the output gate. This produces A, the short-term hidden state used for the immediate prediction and the next time step. Processing an entire document relies on this 6-line block running recursively, 1 token at a time. This chart maps our Python code directly to the theoretical symbols. Looking at the bottom formula, our F, U, and G variables are the literal implementation of the forget gate, the update gate, and the candidate state. While this additive math solves the vanishing gradient problem, it carries a heavy cost. Calculating 4 dense weight matrices at every single time step is computationally expensive, which is why engineers often seek lighter alternatives for the largest models. To process sequential data with true memory, that parameter density made it a tough sell. First published by Sepp Hochreiter and Jürgen Schmidhuber in 1997, the architecture was simply too demanding for early hardware. It sat mostly idle in academic papers for nearly 2 decades. Computing power eventually caught up. In 2015, Google scaled the architecture for their voice search and saw speech recognition errors drop by roughly 49%. A year later, Google Translate stacked these networks together. Translation errors fell by 60%, and the system immediately began serving billions of translations every single day. The hardware tax was steep, but the returns were undeniable. The heavy parameter count was exactly what engineers had to pay to solve complex sequence tasks at a global scale. The applications quickly expanded beyond language. Developers used it for time series data, predicting everything from stock market fluctuations to regional energy demand. It proved highly effective at monitoring continuous streams of information, scanning live Internet of Things sensors to flag equipment anomalies in real time. Its utility covered both structural and creative tasks, driving handwriting recognition software on one end and algorithmic music generation on the other. Look at this schematic of the cell itself. The structure relies on 4 distinct linear operations at the bottom, which calculate what to do with the data, while that central line passing left to right accessed a primary memory conveyor belt. Pushing data through that specific arrangement of nodes and operations became the absolute industry standard for handling any information where order and time matter. This diagram illustrates exactly why the cell succeeds. While a standard recurrent network overwrites memory at every word, the orange timeline shows the cell state carrying the subject's gender, she, untouched across 5 words to predict the proper verb. Because updates to that main line are additive rather than entirely overwritten, the cell creates an uninterrupted information highway. Error gradients can travel backward through hundreds of steps without shrinking to 0. The gates inside the cell learn precisely when to open and close. This allows the network to process variable length inputs naturally, without relying on rigid, predetermined data sizes. It remains a heavily utilized, battle-tested option for environments with modest-sized datasets, or on-device streaming tasks where resources are strictly constrained. By resolving the vanishing gradient problem with an additive memory track, but that same step-by-step processing creates a severe structural bottleneck. The network can only look at time step 2 after it finishes time step 1. Because it is strictly sequential, you cannot parallelize the training process across time. And even with the protective gates, the memory capacity has hard limits. When fed extremely long contexts spanning thousands of tokens, performance rapidly degrades as the internal state becomes saturated. You also have to account for the structural bloat. Those 4 internal gates require roughly 4 times the parameters and computing resources of a standard recurrent cell. If you apply that parameter-heavy architecture to a highly simplified problem or a very small dataset, you run a high risk of overfitting the model to your training data. The strictly sequential dependency imposes a hard mathematical ceiling on processing speed. For engineers working today, the deployment rules are clear. You should avoid this architecture for large-scale, massive language modeling tasks. Those massive natural language workloads now strictly belong to attention mechanisms and transformer models, which capitalize on parallel training and vast text corpora. However, you should utilize this network for time series forecasting, real-time edge computing, and on-device sequence processing, where models need to run locally and efficiently. It is no longer a universal hammer for every sequence problem. It is now a highly specialized precision tool for environments demanding stability and efficiency over raw, massive scale. The technical foundations for understanding this architecture are detailed in the book 50 Algorithms Every Programmer Should Know by Imran Ahmad. The design introduced a crucial concept to machine learning. While a basic recurrent neural network simply forgets over time, this advanced structure actively learns exactly what it should remember. But as engineers optimized their systems, a question emerged. Is the heavy computational weight of 4 gates and a separate, dedicated cell state always mathematically necessary? Research eventually produced a lighter sibling algorithm, one that fuses the operation down to 2 gates and drops the separate cell state entirely to save compute. Understanding the meticulous engineering of the long short-term memory cell is the prerequisite for deploying that leaner, highly efficient successor, the gated recurrent unit.